Hey there, let's practice for test number 2 for fluid mechanics. Okay, Branson is going to play a prank on Drumpf by siphoning the jet fuel out of his private jet. Because Drumpf built a 12-meter high wall around his jet, Branson needs to be careful about cavitation. Ignoring frictional losses, what's the fastest flow velocity Branson can use to siphon gas out of Drumpf's jet if its fuel surface is 2 meters above the ground? And what elevation above the ground should Branson hold the other end of the siphon? Note, jet fuel has a density of 840 kilograms per cubic meter with a vapor pressure of 8 kilopascals. For this question, use an atmospheric pressure of 101 kPa and G is 9.81 meters per second squared. Okay, analysis. We have no frictional losses. That means the Bernoulli equation is justified. Put that in there. And what we're going to be doing is having jet fuel siphon from this gas tank over this 12-meter high wall. At the top point of the wall, we have to be careful about cavitation. That's going to be the lowest pressure point because we will have had a negative, a change in Z moving up. If we've raised Z, then the pressure must be lower if the velocity is constant all the way along the siphon. So that's why we're going to have to be careful about too low of a pressure at the top compared to atmospheric pressure. So atmospheric pressure is 101 kilopascals. If we've moved up 10 meters, then the pressure inside the siphon will have dropped by a certain amount because of that elevation change. So 10 meters up, we're going to have moved by the density times G. So G is about 10, and then another 10 meters, so 100 times this. So that's 84 kilopascals, what we're going to get. So we're going to have moved by 84 kilopascals at the top of the wall. Now, that means we're going to be a lot closer from this 101 to the 8 kilopascals of vapor pressure. So we have to be careful not to raise the velocity too much. So that's what we're going to worry about. Now, the other end of the siphon, when the siphon is low enough, the lower the siphon is, the faster the fluid is going to flow, as long as it's below 2 meters, which we need for it to flow at all. If the other end of the siphon is at the same surface as the tank, then there's no motivation for it to flow because the pressure, there's no actual pressure difference from one end of the siphon to the other. Okay, so let's take some points. Let's let point 1 be the top of the tank, where the pressure is equal to P atmosphere, the velocity is equal to 0, the height is equal to 2 meters. Let's use the ground as a reference point. Point 2 is the top of the wall, where the pressure is, we don't know, the velocity, but we need the pressure there to still be greater than 8 kilopascals to avoid cavitation. Otherwise, the gas is going to start to split up. The jet fuel, I should say, is going to start to cavitate, form pockets of air, and that's going to stop the siphon from happening. The velocity is to be determined, and the Z is equal to 12 meters. And we've got also point 3, which is the other end of the siphon, where the pressure is, again, the atmospheric pressure. The velocity is, maybe we'll give a variable to this, the siphoning velocity. And the Z is also to be determined. Let's give a name to that, Z end. Okay, so what we need to do is choose Z end, choose the height at the end, so that the velocity isn't so big that cavitation happens at the top of the siphon. But other than that, we need the Z to be greater than 0, right? You can't have, or I guess greater than equal to 0 if we're going to put it right at the bottom. Depends on what Branson's trying to do here. Is he trying to empty the jet fuel into another tank, or just have it pour over the ground so that there's no jet fuel in the private jet? Depends. Okay, so how spiteful is Branson in this scenario? So let's try and do some calculations here. So we've got that the, let's start off by equating certain points to other points to calculate the maximum possible velocity. We'll equate 1 and 2. And then once we have that, we'll set z appropriately to get that velocity. Okay, equating points 1 and 2 then. We've got that the atmosphere, let's put in our variables. 101 E3, rho is equal to 840. We've got we also need G, 9.81. Didn't tell us to use a different G, right? Okay, 9.81, perfect. So that means we can do our calculations by substituting in the values at point 1 compared to point 2. So on the left-hand side of the equation, we've got P atmosphere over rho plus 0 plus G times 2 is equal to P top plus P top over rho plus VS squared over 2 plus G times 12. And just substituting in what we know. Now, with everything else subbed in, we can solve for what the velocity should be, so that what the velocity would have to be for the pressure at the top to be equal to the saturation pressure. So let's solve subs P top is equal to 8E3 into that equation. And it tells us that there's 2 possible answers for the velocity, which is either -5 or 5 meters per second. Okay, so now that we know that, we're going to say Vs max is equal to that. That's the maximum velocity that we can have before cavitation will start happening. Now, do we actually get cavitation? Well, we're going to use another Bernoulli equation for this. So we're going to equate the starting condition at the top of the tank, let's say, to the other end of the siphon. So comparing those two, we've got the same pressure on each side, so we don't even need to bother writing that. That's going to cancel. We've got 0 on the left, and on the right, we're going to have 2. So let's just say G times 2 meters is equal to same pressure, so Vs max squared over 2 plus G times Z end. Let's see what, and think for a moment about what this is going to tell you. This is going to be an equation where if we use the max velocity that's allowed, we will determine what the minimum height allowed to avoid cavitation will be. So we can say solve that thing, and it tells us that the minimum height allowed for cavitation is 7.14. So there we go. .714 meters. Since this is greater than ground level, we can use this. But any lower will make the velocity higher than 5.02 meters per second, which would make the pressure at the top lower than 8 kilopascals, 8 kPa, and therefore cause cavitation. Stopping the siphon. Explain how you expect the energy grade line and a hydraulic grade line to behave for flow through a partially open valve. Same pipe diameter on either side. A, if the Bernoulli equation is valid, which means no frictional effects, and B, in reality. Okay, so if the Bernoulli equation is valid, then EGL is constant. But HGL, the hydraulic grade line, will rise if the velocity drops and vice versa. So it'll lower as the velocity rises through the valve. Since the volumetric flow rate has to be a constant as we're moving across the valve, then because the valve partly open has a smaller area, it has to have a higher velocity, which means the HGL, which doesn't include the velocity part, has to be lower. Let's just remind where that information is. So let's see, did we put that in the summary note? Yeah. Okay, so energy grade line, EGL, was the energy head. So it's just the Bernoulli equation expressed in terms of head, the entire thing. And the HGL is this without the dynamic part, so the static and elevation pressure head. So if this is a constant and the velocity goes up, then this part must be going down. But rise back up again to its initial value after the valve. In reality, though, there's losses across the valve. With losses, EGL will drop across the valve, especially during the expansion. Expansions are a lot worse for energy losses than contractions. So on most of the losses happen as the fluid is leaving the valve and going back into the reservoir from its faster velocity. For HGL will drop again into the valve, even lower than before, due to the losses, and not rise up quite to its initial level. The difference being equal to the drop in EGL. Why is that? Because the velocity is going to be the same on both sides still. So the loss in EGL will actually not be taken up by a loss in velocity. What will it be taken up by? Well, the Z is the same on either side, so it's not that either. The losses in energy appear entirely in the pressure. And this is why for any real frictional pipe, any pipe that has friction in it, you need a pressure difference across the pipe to cause any fluid to flow from one side to the other. Velocity is constant all along the way, the Z's constant all along the way, and so a pressure difference has to account for any energy losses. All right, final question on this test. Niagara Falls is 51 meters high, total over several drops, and is fed by the Niagara River with an average flow rate of 5,800 cubic meters per second. To keep the falls looking good, not all of this is used for electrical power. Water is diverted to maintain a steady stream of water going over the falls at all times, meaning that you don't have all of the water for electrical generation. All that we have for electrical generation is an average of about 3,900 cubic meters per second. Now, suppose the power plants at the falls have a combined output power of 1.5 gigawatts on average, so that corresponds to this flow rate, and their electrical generator efficiency is 90%. This is the efficiency for converting the mechanical kinetic energy into electrical energy. Determine the total head loss to friction for the water that's used for electrical generation, and the temperature increase of the water that's used for electrical generation, assuming all the frictional head loss ends up as heat in the water in steady state, and the temperature increase of the water that doesn't flow through the turbine, so it just goes over the falls, the more beautiful water. Possibly useful information is the density of water, that G is basically 10, the air pressure is about 100,000, and the saturation pressure of water is 2.34 kilopascals. I don't think that'll be important. And the heat capacity of water is 4.2 kilojoules per kilogram Kelvin. Note, assume water has approximately the same kinetic energy entering the top of the falls as it does leaving the bottom of the falls for all parts of this question. So what we're going to do is take our energy equation in terms of head to explain what's going on here. So this picture from the textbook is awesome. What we've got is no pumping here, but we've got a mechanical of the fluid going in, and then we're going to be having some mechanical of the fluid going out at the bottom of the falls. We've got some head loss, and we've got the rest of the energy going into the turbine. So let's get our information there to answer the first part of the question. Okay, so at the top and the bottom of the falls, what's the same? We have the same pressure, so we can cancel that with this pressure term over there. We have the same kinetic energy. They told us to assume the water has the same kinetic energy entering the top as it does leaving the bottom. So that's done. That's a lot easier. We have a height difference. There's no pumping going on. So we're left with just a height difference. So the higher height, let's say at the start of the falls, has to be responsible for the head loss that happened because we put work into turbines and the head loss that happened from frictional factors. So what we have is, maybe let's rearrange this. Z1 minus Z2 is equal to the rest of these quantities. Now, our goal is to calculate this. So maybe we'll rearrange it in terms of that. This would equal 51 meters minus the useful head that went into the turbines. So the head loss to turbine energy generation there. So how do we figure out what this is? Well, that we can determine with the information about the power generation and the efficiency and also the flow rate. So going back to our topic summaries document there, the power generation is related to the mass flow rate times G times the corresponding head that was going into power generation. So the head loss corresponding to this power generation. If you have a certain mass flow rate and a certain mass flow rate going across a certain energy per mass flow rate, then multiplying them together will give you the power. Okay, so what we can say is that the head may be applied to the turbine is then H turbine is equal to the useful work divided by m dot g, and let's see what we have there. So the actual mechanical work that went into the turbine is not necessarily the electrical work, so it's 1.5 gigawatts, but then multiplied by the efficiency. There we go, eta. So the 90%. Let's think that this makes sense. We didn't get all of the, well, actually, hold on a sec here. We've got 90% efficiency for converting this mechanical work into electrical work. So rather, we can say that the actual work that we must have generated must have been this divided by 90%. Because the electrical energy that we get out is going to be less than the amount of mechanical energy we must have had to have put in to get that. So this is what's going to give us a number that's bigger than the 1.5 gigawatts, and that's how we're going to be conserving energy. We do lose some to heat in this electrical generation. So then we can divide this by m dot, which is rho times the volumetric flow rate. So volume with the capital, with the sort of script V there, times G. Oh, we want a regular G for that. Yeah. And the volumetric flow rate is what they actually gave us. So 3,900 cubic meters per second. Okay. So now we can substitute into this and get the useful, get the head that was applied to the turbine for substituting into this formula. Let's just do a unit check here. We have watts, which is a joule per second. We've got, in the denominator, kilogram per meter cubed. We've got meters cubed per second for the flow rate. And we've got G, which is newtons per kilogram. Okay, so a joule is a newton meter. Newton meter per second. The per second is going to cancel in the denominator, and the newtons are then going to cancel. Kilogram cancels, so we would end up with just newtons, or rather, just meters. Okay, that's good. So that's exactly what we were hoping for. The effective head loss that happened because of the turbines is going to be determined by this formula after we substitute in everything that we were given here. And we would expect that it's going to be somewhat less than 51 meters. Let's see what we end up with. Okay, so we'll get our calculator out here, and we've got 1.5E9 divided by 0.9, and then we're going to divide that by 1E3 times volumetric flow rate, 3,900. And then multiply that by 10. So we have 42.7. Oops. Let's try that again. 42.7 meters. Okay, so that means that our head loss to friction is then where the rest of the height went. So if we started with 51 meters, if we had 51 meters of elevation head in the difference from the top to the bottom, and we spent 42.7 meters of head generating this electrical power for that flow rate, then the rest of the head difference must have gone into frictional losses, and that would be 8.26 meters of head loss. Okay, so that's it. That's part A. Okay, part B. To do this part, what they ask is figure out how much of a temperature increase this head loss to friction corresponds to. And to figure that out, we're going to need to make use of this heat capacity term for water. So this parameter that lets you convert to figure out how much energy is associated with a certain temperature change. So let's see how this works. This gives you an energy for a certain mass and a certain temperature change. So if instead, in the case of fluid flow, we have a mass flow rate, then what we're going to be getting at the end is not an energy, but we're going to be getting a power or an energy flow rate. So that is what's going to be equivalent to our standard energy flow rate term, the power term associated with a certain head loss. So this gives the information for how we can translate that head loss term into a temperature change. So what this means, if we rearrange things, is that the temperature change is equal to G times the head loss divided by just Cp. The mass flow rate cancels out on both sides. Let's check that the units make sense. We've got G times the head loss. So this is not energy terms, but this is energy per unit mass, if you think about how gravitational potential energy works. So energy per mass, and then we've got energy per mass temperature on the denominator. So we're left with temperature overall. Okay, all good. So all we need to do then is take the head loss, multiply by G, and then divide by the specific heat capacity. All right. So with movie magic, I've gone ahead and done that. All ready for us here. So we've got the head loss that we just calculated multiplied by 10 divided by 4200, and we got 0.019. And if we use for part C, the entire height of the falls, so the water that just goes over, all of it gets converted into heat. So we'll just take 51 times 10 over 4200, and you see 0.12 degrees as opposed to 0.197 degrees. So the water that goes right over the falls heats up by a fair bit more than the water that gets used for electricity generation.